Hey everyone, in Chemistry 1111 Universe, it's Dr. Carroll here. We are looking at Unit 4, Lecture 2, Absorption and Emission Spectra, part of our quantum theory. We recall last time we talked about the photoelectric effect where you completely kick out an electron from a metal surface. But what if you put an energy and don't quite kick it out? So the electron could have started in its most stable energy state, a ground state, and get into an excited state. That's an absorption spectra. Then when the electron falls from an excited state back to a ground state or back to any state lower than the excited state it started in, that is an emission spectrum. So absorption and emission spectrum helped chemists understand how the energies are quantized, are in discrete values in an atom, and also helped identify one atom from another. So absorption and emission spectra became diagnostic tools, also used in astronomy, which is sort of cool. So I'm on page 174 in the textbook, so I'll use that, and our lovely PowerPoints will help as well. So the absorption of photons by free electrons, here I am, has two different results depending on the energy of the photon. When an atom absorbs a photon of sufficiently high energy, an electron is ejected, kicked out, photoionization. Photo means light, right? So you use light to ionize and kick the electron out. If the atom gains energy but does not ionize, then it is transformed into a higher energy state called an excited state. Atoms in excited state subsequently give up their excess energy to return to the lower energy state. The lowest energy state, most stable, is called the ground state. And we're going to use the letter N to represent the energy levels in a hydrogen atom. So N equals 1 is what we call the ground state. And N equals 2 is the second energy level, and it's called the first excited state. N equals 3 is known as the second excited state. N equals 4 is the third excited state. And onwards from there until you get to the infinitely high energy level at which the electron is kicked out, photoionized, if we're zapping it with EMR. Okay? And the energy needed to go from, let's say some people use like me, I like to use a half arrow for an electron. Let's say you go from the first energy level, it's ground state, to the second energy level, which is the first excited state. So you put in a photon, h nu, to kick it up. The amount of energy needed to do that is the exact opposite the amount of energy needed when it falls back down. Okay? And the energy levels get closer and closer to each other as you go up to the infinitely high level, and we'll see the math behind that a little later, either this lecture or the next. And the bigger the jump down, the more energy is released by the photon. Okay, so let's see some pictures here. These are energy changes relative to the energy of free electron. By convention, scientists define the energy of free stationary electron to be 0. So here, this is basically what I looked at already, okay? And then you have, here's my ground state and various excited states. Don't worry too much about that heat loss. Okay. A bound electron has negative energy only in relation to a free electron. Fine. Atomic energy transformations can be represented using an energy level diagram, such as the one that I drew, or on figure 9. Okay. And excited states don't stay as excited states. They want to lose energy. They lose their excess energy in collisions with other atoms or by emitting photons. Oh, that's where the heat loss came, just by colliding with other atoms. The key feature, which I've already mentioned, in the exchange of energy between atoms and light. That's what spectroscopy is. Interaction of atoms and light is that energy is conserved. This requires that the change in energy of the atom exactly equals the energy of the photon. So delta E of the atom is plus or minus h nu of the photon that came in, plus if it's absorption, minus if it's emission. Okay? Sometimes the energy can be lost in a series of steps. The total amount of energy lost, you just add up the energy in each one. So let's look at an example here. Sodium vapor street lamp emits yellow light at a wavelength of 589 nanometers. What is the energy change for a sodium atom because of that, and how much energy is released per mole of sodium atoms? Okay, so we're giving out photons, so you use electricity to zap electrons to higher energy levels, then they fall back down and release energy. Sodium atoms lose energy by emitting photons of 589 nanometers. So the energy of that photon is hc over lambda. Energy is conserved. So the energy loss of the photon can just be written as minus E photon. The equality includes a negative sign because the atom loses energy. So we just get the value for hc over lambda, and that's the amount of energy lost. Okay, so the book made it a bit too fancy. I would just go straight to hc over lambda. It says hc lambda, and I get that the energy carried away by the photon is 3.37 by 10 to the minus 19 joules. The negative sign means energy is released. So the atom has gotten more stable by spitting out photons, and those photons to our eyes look yellow in color. Okay, and that's one sodium atom emitting one photon. To get per mole of photons, you take that one value, 3.37 by 10 to the minus 19, and you multiply by Avogadro's number, 6.02 by 10 to the 23. And you get 203 kilojoules per mole, or 2.03 by 10 to the 5 joules per mole. So that is the energy released per mole of atoms. The energy change is negative, as required by the fact that the emitted photon carries energy. Okay, let's try one together. Mercury lamps emit photons with a wavelength of 436 nanometers. Calculate the energy change in the mercury atoms in joules per atom and kilojoules per mole. And then if you looked at a picture, it turns out mercury is bluish in color, blue in color. So all we're going to do here is we're going to take delta E is going to be hc over lambda. Okay, we're falling because it's an emission, so I can put a negative sign there. Different ways to do it. 6.63 by 10 to the minus 34 times 3 by 10 to the 8th. You want a negative sign? Go ahead. Over lambda, 436 by 10 to the minus 9. That's going to be joules associated with one photon. So let's punch that out here. 6.63 by 10 to the negative 34 times 3 by 10 to the 8th divided by 436 by 10 to the negative 9. And I get 4.56 by 10 to the minus 19 joules. And when I get kilojoules per mole, I'll take that number and I'll multiply this by 6.02 by 10 to the 23, and then I'll divide by 1,000 because I want kilojoules, not joules. So 274.63 kilojoules per mole. And that 436 nanometers is blue. So mercury lamps exert blue colors, sodium lamps exert yellow, and sometimes some street lights I'm sure have mixtures of different filaments in them, sodium, mercury, potassium, whatever. I don't know, potassium, really? Well, anyways, you can do some research on that if you want and find out what different colored streetlights there are. Atomic spectra. Okay, let's first go to let's look on the slides. Just got to see if there's something extra maybe on the slides. No. Atomic spectra, atoms can absorb and emit radiation. Absorption, usually a source of white light passes through a sample and the atom absorbs specific frequencies of light. An absorption spectrum measures the frequencies of photons that an atom absorbs. Emission is the more common one. When excited atoms emit photons, the frequencies of the photons are specific. It's not some blurred values. The specific lines is what you see. The emission spectra are also called line spectra. An emission spectrum plots the intensity of light as a function of frequency. Okay, well, I'll use the slides for a second. Keep going with that. This is a nice slide. So you have here a lamp which has been excited. Electricity is running through it. Then you try to focus a plane of light through a gas. Okay, so that's my source, and this is one way of doing absorption spectra, and then you get a pattern, a light pattern. And this isn't the common one. Here's the common one. Common one is this one here, the emission spectrum, where you have the gas discharge tube. It goes through a opening, and then you get a screen here which has distinct lines. In this example, these four, this is hydrogen, I think, yes, hydrogen is the one used here. These four lines are corresponding to electron transitions from one higher energy level to a lower energy level. In fact, these are going from the sixth, fifth, fourth, and third energy level down to the second energy level. There's other transitions that happen, but those four are the only ones that are observed in the visible spectrum and that light up this photographic film, if that's the matter in which you're doing it. Okay. So the question became, why do atoms only emit photons at certain frequencies? And that was the whole business about the quantization of energy. Most elements are complex and show little regularity, but Palmer first described the hydrogen spectrum quantitatively and came up with a equation. We won't use that equation really, we'll use a better one, a more common one. So the emission spectra gave Bohr enough ammunition to come up with the idea that we have the thought that the electrons are orbiting the nucleus at certain intervals, discrete energy levels associated with those orbits, and that is what we call the Bohr model of the hydrogen atom. Okay, that's where the word orbital comes from, because the electrons are orbiting there. Okay, let's go back to the textbook for a second before we, a little mini text, not our text. So there's atomic spectra and emission spectrum. Emission lines appear bright against a dark background. Spectrum shows this is the emission spectrum for hydrogen atoms. Now each element has a unique absorption and emission spectra, its own set of characteristics, because it has its own set of energy levels different from other atoms, right? There's differing number of electrons, there's differing number of protons, so you can't expect the energies of every electron in every atom to be the same as every other electron in every atom. It doesn't work that way. Now, our spectra are pictures in the visible spectrum, but there's others, like we said, and other machines can do that. So here's, you see sodium, and you see this yellow line here. Here you see neon, a bunch of them. Red's more intense. If you just plug neon light in it will be red. Now you can say, oh no, it's all sorts of different colors. Yeah, well, sometimes in Las Vegas they mix neon with other gases, or you frost them with different coatings, and you get all sorts of different colors. But neon itself, what we see the most intense is red. But you see there's all these different lines here, but it's not a whole blur. It's just these different lines involving transitions from higher energy level to lower energy level. Mercury, the blue lines are the most common. Okay. So let's go on here, and we talked about the energy changes of an atom equaling the photon h nu. Hydrogen, so this was Johann Balmer who came up with this equation. It's 3.29 by 10 to the 15 reciprocal seconds. That's a constant times 1 over the initial energy level the electron is, minus squared, minus 1 over the second one squared. But then Bohr, as we said, worked around that interpretation, and Bohr realized that the emission frequencies have specific values because the electrons in a hydrogen atom is restricted. That's the big word, restricted to specific energies. And here's the equation. You don't have to memorize it. Minus 2.18 by 10 to the minus 18 joules over n squared. Now some of you may remember another way of writing it. The energy of an electron in a hydrogen atom is minus 313.6 over n squared kcals per mole. Well, it's also minus 2.18 by 10 to the minus 18 joules over n squared. Negative sign reflects the facts that bound electrons have negative energies relative to a stationary free electron. So, this is for one atom, and n is not 0. The ground state n is 1. Then you go up in natural numbers, 3, 4, 5, 6, 7, ... Bohr's idea of restricted energy levels was revolutionary because scientists at the time thought that the electron and hydrogen atom could have any energy at all, not just the ones described in this equation. But Bohr said no, only specific values are allowed. And a property that is restricted to specific values is said to be quantized. Energy levels of any elements are quantized. Okay, so the lowest level, ground state, would be minus 2.18 by 10 to the minus 18th over 1 squared. The fourth level, minus 2.18 by 10 to the minus 18 over 4 squared, etc. Okay? So the change in energy when you go from one energy level to another is just the final value minus the initial value. And photons always have positive energies, but energy changes can be positive or negative. If it's absorption, atom gains energy, photon disappears as it transfers its energy so that the atom gets into an excited state. If you've got emission, the atom loses energy, so the change in energy for the atom is negative, and a photon appears. So it's best just to say the energy of the photon, either absorbed or emitted, is just the absolute value of the change in energy for the atom. That's an easier way to talk about it. So let's see how this all works in example 4.6 on page 179. What is the energy change when the electron in a hydrogen atom changes from the fourth energy state to the second energy state? Sometimes you hear that as written as fourth energy level down to second energy level. But fourth energy state to second energy state is good. So our n initial is 4, our n final is 2. You want to get what's the wavelength of the photon emitted. So we want to get the energy change and the wavelength. Okay, so the energy difference is the second energy level value minus the fourth. The fourth one we already said is minus 1.36 by 10 to the minus 19. The second would be minus 2.18 by 10 to the minus 18 over 2 squared, minus 5.54 by 10 to the minus 19. So the difference, final, minus 5.45 by 10 to the minus 19, minus initial, which is minus 1.36 by 10 to the minus 19. And you see that this is a release of energy. How much? 4.09 by 10 to the minus 19 joules is released. This energy change is negative because the atom loses energy. This loss of energy appears as a photon whose energy is given by equation 4.6. Okay? To determine the wavelength associated with that energy, so we got 4.09 by 10 to the minus 19 joules. E photon is hc over lambda, so lambda is hc over the photon. Hc over the energy. Now, this question wasn't asked explicitly, but the wavelength is given in nanometers here, so you have this conversion to nanometers. So that's how it's done. Okay? What energy and wavelength must a photon have to excite a hydrogen atom from its ground state to the n equals 4 level? Now I'm going to show you a little shortcut to do this one, or to do these in general. You can just write it like this. Delta E, I'm going to combine them together, is minus 2.18 by 10 to the minus 18 times 1 over n final squared minus 1 over n initial squared. So if you just want to get the transition energy from n initial to n final, it's minus 2.18 by 10 to the minus 18 times 1 over n final squared minus 1 over n initial squared. So it'll be minus 2.18 by 10 to the minus 18. Now, ground state's at n equals 4 level. So 1 over 4 squared minus ground state 1 over 1 squared. So you'd get 1 divided by 16 minus 1, and multiply that by 2.18 by 10 to 18 minus. So you get 2.04 by 10 to the minus 18 joules. Okay, see, this is a faster way of doing it, isn't it? So that's the energy. The wavelength, well, lambda, we already had a little lambda, hc over E equals hc over lambda, so lambda is hc over E. We just got E. H, 6.63 by 10 to the 34 minus, speed of light, 3 by 10 to the 8th meters per second, divided by the energy that we just got, 2.04 by 10 to the 18 negative, and I get 9.75 by 10 to the minus 8 meters. Which becomes 97.5 nanometers. Okay, so that's how that works. Now, let's look at these energy level diagrams. Okay, this is just too much discussion here. We just look at a staircase, but the staircase isn't a good example because the stairs are going to get progressively smaller and smaller distance between them. Okay, so anyways, but just the general idea, separate allowed energies. You have a ball on a staircase that's in the ground state, you can zap it up to a higher level, and then it can start to fall down, maybe all at once or maybe in a series. Here we have energy level 1, 2, 3, 4, 5. I could go from the 5th level all the way down. Oh no, this is an absorption one. First level all the way up to the 5th. So the energy difference between 5 minus energy in the 5th minus energy in the 1st. Or here we can have a emission. Oh, I see it's being paralleled here. Where I go from the 5th level down to the 3rd. And energy is released. And the energy taken away from the transition from a higher energy to a lower energy is the photon emission. Okay. Elements other than hydrogen also have quantized energy levels, but they lack the regular spacing that we saw in equation 4.5, so they're more complicated. But you can get spectra for every atom. Here is a beautiful picture, isn't it? What page is this in the textbook? This energy level diagram. Page 180. So we have here our n value. This we're going to learn is called the principal quantum number. So the infinitely high level, here's my first level, second, third, fourth, fifth, sixth, etc. You see, because of the n squared term in the energy, I mean, it's proportional to 1 over n squared, right? I know it's to minus 2.18 by 10 to the minus 18, but just proportional to 1 over n squared. If it was proportional to 1 over n, then all the spacings would be the same. But it's 1 over n squared, so the values get smaller. So we have here absorptions, and we have emissions down to various energy levels. And you actually form series. If you fall from higher levels down to the first level, that's called the Lyman series, which from n equals 6, etc. down is ultraviolet. If you go down to the second energy level, from energy level 6, 5, 4, 3, 2, those emissions are actually in the visible spectrum, and that is known as the Balmer series, in honor of Johann Balmer. If you go from a higher level, go to the third level, that's infrared, and that series of lines is called the Paschen series. Go to down to the fourth level, it's called bracket series. Fifth level is called Fund. So going down to the fourth level is bracket. Going down to the fifth level from higher ones is Fund. So here's a mnemonic device that I've used. I mean, I think the most you'll have to know is up to the Paschen series in terms of the names of the scientists associated with the series of lines, whether we can see them or not. But a thing I made up is a mnemonic devices. You ready? Here we go. So he was an offensive lineman for the Blue Bombers. Therefore, he played with lots of passion. But he played in the Canadian Football League, so he was in a very low tax bracket. But he mostly just played for fun. Okay, you gotta like that. I bet there's no one else in the universe who has come up with that mnemonic device to mention the first 5 series associated with emissions in the hydrogen atom. If you know someone else who does, let me know. I want to high-five that person. I almost said shake the hand, but I don't know anymore about all that stuff. Okay, here is a more complicated situation. This is mercury, so you see there's a difference in spacing, so you get different series of lines, and not all of them are in visible or ultraviolet. They're all over the place. Some in ultraviolet, some aren't. But they still are quantized. There still are lines. They just aren't in exactly the same place as the hydrogen. Okay. I never liked this example. I'm not going to bother with this example. Yeah, neither of those examples. I'm not quite sure why those examples were even put in there. So omit example 4.7. The wording is it's adding some stuff that we don't need to add. I mean, there's enough other examples, so don't worry about those ones. Let's maybe look at here. No, I don't like that one. Don't like that one either. Let me just make one more example. Sometimes I do this. Watch this. I'm just going to, before I go to properties of electrons, I'm just going to make up a question. So I'm going to go to my canvas here, my paint.net, and I could say something like that, like this. Which transition in a hydrogen atom emits a photon with a shorter lambda? 6 to 5 or 4 to 1? Okay, shorter wavelength. What does that mean? What does that mean? Shorter wavelength. That means a higher frequency, more energy. So it's got to be a larger drop. And from 4 to 1, right? Here's 1, here's 2, here's 3, here's 4, here's 5, here's 6. Okay, but 1, 2, 3, 4, 5, 6. Going from 6 to 5, that's a smaller jump down than going from 4 to 1. Whoa, that's a bigger jump down. 4 to 1, much more energy is released than going from 6 to 5. Well, if more energy is released, then it is a shorter wavelength, and it's a shorter wavelength. Then that's your answer. 4 going down to 1. Okay. So that's good for this second lecture. And we'll talk about, we'll just start with energy level diagram. We're going to talk about the actual neighborhoods in which the electrons live in our next lecture.